Now we will start talking more about black holes and stuff. So, check your grade, uh, which I said in class, but I didn't say it on the video. So, for the video, please go check your grade uh, and make sure that there's nothing missing, or there aren't any points that are wrong, or errors of any kind. Also, check that you're not missing any assignments. So, spectra, open. There you go. And we'll close you. You go over here. There you go. Right. So we talked about so where are we at? We're talking about active galactic nuclei. Active galactic nuclei are galaxies that are really stupid bright, like way brighter than they ought to be based on what we think is in a galaxy. So we dig in a little bit more and realize that there's a black hole, a little tiny black hole, or a great big black hole, depending on what you mean by big, um, at the center of the galaxy that's eating a lot of stuff, and as it eats, it shines brighter than the sun, brighter than a galaxy full of suns. So we're talking about the various pieces of the spectrum of an AGN, going from the radio all the way at the long wavelength, low energy photons, and we'll go all the way up through the X-ray. So next we're going to talk. So we talked about synchrotron. Synchrotron is hot electrons spiraling around magnetic fields. They give you radio photons. We talked about the continuum, which is kind of the background that everything sits on in the spectrum. And it has a shape to it. That shape is a bunch of black bodies added up together. You remember when we derived the disk, we derived the accretion on the disk, we showed that the temperature goes like r to the minus 3/4. And at every radius, you have basically a black body because it's basically a thermal equilibrium. Okay, now it's rattling around like crazy. A real disk is not actually in any kind of equilibrium, but we're going to run with that for now because that gets us most of the answer. So the continuum from the IR through the UV is all set by the disk. And so there's a couple processes of the disk. The one that I care about most for you guys is the bunch of black bodies. Now I'm going to talk about the broadline regions, which are a little bit more complicated. So first off, let's talk about what it is, why it's so wide, what the density is. Now, we don't talk about volume density a ton in this. We do sometimes, but it's hard to measure. So we need some extra probes to measure the volume density of the gas. Density of the gas tells you a lot about what's going on in it. If the density is 10 to the 9, then you know it's inside of a star, and if it's 1, you know it's in the middle of the galaxy. So we'll learn about the density, and we'll learn about the structure of these things, and then we'll talk about what we can do with them. So here is one of the spectras in the book, and you look at this oxygen. This is oxygen, I think that's 7. That's a very strong line. This is a spectra, so this is flux vertically and wavelength horizontally. So this is a line. This is some oxygen that's very bright, and here is H beta. So this is hydrogen beta. That's the second. That's the 3 to 4 transition in hydrogen. Oh wait, no. Maybe it's the 4 to 2 transition. Anyway, I'm not gonna check you on that, so I don't care. It's one of the hydrogen transitions. But you see how much wider this is than this one? Let's look at some of these other things. So here is Lyman alpha. Do you see how wide this spectrum is? I mean, this is very large. So why so large? So when I have a spectrum, let's draw a picture. My spectrum is set by, so cool. My spectrum is set by the Doppler shift of the stuff and the physics of what's going on at the center. So I have some flux, that's a function of lambda, and I have my lambda, and if I have a blob of gas that's emitting in, say, hydrogen alpha, if it's not doing anything, I just get a delta function in my spectrum because all of the gas is emitting at that frequency, the energy of that transition. So this is energy over H is the frequency of the transition. But if I have some temperature, that gets wider because things have kinetic energy. So temperature is a measure of the kinetic energy of the molecules in the thing. So if it has some temperature, then we'll have some width. And if it's moving like crazy, we can get some width from that too. So let's sort things out. So 1/2 mv squared is roughly approximately equal to kT. We really need a 3/2 there, but since we're going to get a number that's ridiculous, the 3/2 doesn't matter. So, so what is the width of this line? The width of this line, it's some wavelength, delta lambda, right? We can turn that into a velocity because delta f over f is delta v over c. So delta lambda is just going to be units. Is going to be, this is in meters, so that's got to be delta v over c. Is that right? No, c over v. Right. So there's a relationship between how long it is and how fast that gas is moving, right?
I think, oh yeah, that would be better, just kind of cramped.
Yeah, I can help you get a spot of it.
I'm sorry.
Okay, so the width of this line is 1/2 mv squared, so the width of this line is some velocity, delta v. So I can turn that, so I know what the width of the line is because I can measure it. So if we measure the width of one of these lines, let's see, did I put any actual numbers on this slide? I didn't. Anyway, I should have put some numbers on this slide. There's some numbers in the book. So from the spectrum, I can get the width of the spectrum, and from that I get a velocity. So that gives me a velocity, and then 1/2 mv squared is 3/2 kT, gives me a temperature. So if I look at these broad line regions and I ask what temperature would give me that line if all of that line width were from the thermal energy, then I would get a temperature of like 10 to the 10 Kelvin, which is too large. Why is this too large? Because you would see anything this hot, it would be radiating like crazy in gamma rays and X-rays. It creates this is hot enough to start creating electron-positron pairs. So that's problematic. So this temperature is way too large. 10 to the 10 Kelvin is much larger than anything that is just going to be naturally there. Supernova get up to a temperature of like 10 to the 9 Kelvin when they're exploding. Biggest explosion in the universe is not this hot. So this temperature is too large. But we can sort out what the velocity is if we just say, let's get a velocity from that. You get a velocity of like 1% the speed of light. Which makes sense. So that's okay. We can get, yeah.
So since thermal energy is also kinetic energy, is the difference between like the thermal and the kinetic part just like individual particles versus like bulk motion? Or
Yes, exactly. So it's individual things rattling around with some statistics versus everything just going like crazy in one direction. So crazy in one direction is where we wind up. That's how this makes sense. So why is it moving so fast? Around? On the black hole. And v squared equals gm over r. So if r is some large number of the Schwarzschild radius, if r is 500 times the Schwarzschild radius or 100 times the Schwarzschild radius, then we get a velocity that makes sense. So v squared is gm over r. N is really big, so v is going to be really big, unless r is also really big, and then you're not around the black hole anymore. Once you're around the black hole, then the velocity is very large. So we get a large velocity because the gas is spinning around the black hole. You don't see this as much with the disks. I'm not an expert on the disk spectra, so this has to, the spinning has to matter as well, but I'm not really sure how that fits in. But regardless, these things are discrete objects. So, um, let's see. Oh, so we can measure. I went through this the other day. We can measure the density of this stuff. So we can see that the gas is moving like crazy. That's from the broad line. That's all we can tell. We can't tell where it is. All we can tell is that it's the width of that line is very large. So we can measure the density of this stuff by looking at the ionization states. And I don't think I need to say anything about that. Where was? Oh, yeah, it is. So here is radiation in 30 seconds. So how do we sort out what the density is? We look at these forbidden lines. Because the forbidden lines exist, we can bracket the density as like a few particles per cubic centimeter, which I don't have on this slide. Huh. Here we are. So we have, when you have a gas and it's in an excited state, there are three ways that it can become unexcited. It can run into something else, it can just spontaneously fall over, or it can get kicked down by another photon. The last one is pretty rare. Those are called masers, or lasers if you have one in your pocket. Spontaneous emission usually happens pretty fast, but for some transitions they're not allowed. So collisional de-excitation is usually what happens. But if the density is too low for collisional de-excitation, then you know that that line exists because the density is low. So if I see some of these forbidden lines, I can tell that the density is low. So that says, well, the density is low, so it's got to be pretty far away from the middle of the disk. So that puts us out at kind of the edge. And we want to understand what do these things look like. Is it just disk out there, or does it have some structure to it? So this is an argument that I'm, someday I will shore this up and make this a stronger portion of the course. So we want to understand what these things look like. So what we're going to look at is the geometry. So we're going to just assume that it's not uniformly filling the region, that it's clumpy, and there's blobs of stuff, and then space with no stuff. So we're going to do two things. So what happens with these broadline regions? And why am I seeing them? Where do I see them? We see them, they're line radiation. So that means they're some kind of gas that's being excited and then radiating it out, and then de-exciting, radiating it out. So something is lighting this stuff up. Something is exciting that line. The thing that excites the line is the UV from the black hole. So I have my black hole here, and here's my disk. And I have UV photons that come off the interior of the inner parts of the disk. I have other photons that come off too, but there's a lot of UV. These UV photons go everywhere. One of the places they go is out here to the broadline region. And that excites other lines. So for instance, there's one that I use later on. Why are you not? There you go. Let's look at carbon 4. So let's say these UV photons. So these UV photons are continuum photons. That means they don't have a particular wavelength. There's a bunch of them, and they're spread out over a whole big, long, wide wavelength. They come out here, and they excite all of these, all of the hydrogen and carbon and stuff that's out here. So one of the things that it can excite is, say, the carbon-4 line. Carbon-4 then radiates from out here. So I can sort out how big these are and how many there are by saying the total flux in carbon-4 is going to be proportional to the number of clouds times the radius of the clouds squared. Why is that? It's going to be proportional to the total surface area of clouds out here. Does that make sense? Because the photons are going to come here, get absorbed by the surface of this little blob, but it's just absorbed by the surface, and then it re-radiates. The H alpha continuum, which also comes from these, this comes from the gas itself. This is going to be proportional to the number of clouds times the radius of clouds cubed. Does that make sense? So the stuff is radiating because it has some temperature. So the clouds are radiating in the broad line, but they're also lit up by the central source, and that's what gives you the actual line. So the line itself is lit up by the interior of the black hole. Oh, my camera's not on. Wonder why that was. So the line is lit up by the black hole. This is an important piece of information that's going to show up again when I talk about reverb mapping. So what happens is I've got this disk, it's feeding the black hole, it's hot and has a bunch of UV photons. It's also clumpy, so sometimes it gets a lot brighter in the UV and dimmer in the UV. It fluctuates like crazy. So the UV photons are all coming from the center of the black hole of the system. The broad line regions are lit up at the end. So the UV photons hit the fluffy little clouds and excite carbon-4. The things also have some temperature, so they will radiate, say, continuum photons on their own. So I can see the continuum photons are going to go like the volume of the cloud, because every particle is radiating. But the line is only going to go like the surface of the cloud, because the surface is what gets lit up by the center of the black hole. Does that make sense? Yeah.
Why is the carbon-4 radius squared, but the carbon H alpha is cubed?
So squared goes like what? What quantity goes like a square of the radius? Area. Area goes like the square.
Yeah.
Or quantity goes like the cube.
Volume.
So the carbon-4 lights, the UV photons excite the carbon-4, but only the stuff on the surface.
Oh, okay.
Because the photons all get absorbed, the UV photons get absorbed, they don't go all the way through the cloud. So the carbon-4 flux is proportional to the UV that got absorbed, which is proportional to the surface area of the cloud, r squared. The cloud is radiating from the interior of the cloud in continuum, and so those are like the top two bands there. And that's coming from the volume of the cloud, which is going to go like the number of clouds times the radius cubed. I want to turn this into a better homework problem, but I haven't yet. Yeah.
Would you also have to take into account any clouds that are covered by other clouds with the surface area one?
Probably. I mean, there's lots of ways. I mean, you want to also take into account the fact that they're not all the same size.
Yeah.
So you need a distribution of sizes.
Only half of them is actually facing the black hole as well. Or are they also possibly rotating?
Yeah, this is a terrible cartoon. Don't make it. You don't need to make this one any fancier. So yes, there are ways you can make this measurement better. So lots of things have to go into account. So the actual thickness of the UV, how far does it actually go in matters. So lots of things matter, but lots of little things kind of go into it. But the bulk is the UV lights up the line, and And that's proportional to the surface area of the cloud. The radiation from the cloud itself is proportional to the volume. We can use these two things. I've got two equations and two unknowns, right? These are things that I measure. These are the things that I want to know. So around a typical black hole, we find about 10 to the 7 little fluffy clouds. And they have a radius of like 10 to the 13 centimeters. I think that's the numbers that I put up there, yeah? Yeah. Bloop. Does that make sense? So what can we do with that? So that's, what else do I need to say about broadline regions themselves? That's it. This is the important bit. Let's talk for a second. I'm gonna, I think, yeah. I'm gonna take a second. I'm gonna talk about reverberation mapping. So, oh, I don't need you anymore. Okay, so how long does it take? So I've got several signals here. I've got the UV signal, which comes from the center of the black hole. I got my line radiation, which comes from out here. I've got several lines that come from out here. There's a bunch of things that come from out there. We don't need to think about the number of clouds anymore. All you need to do is think about, it's a bunch of little fluffy clouds out here, and a disk in here, and someone can prove rigorously that they're little fluffy clouds. I'm not going to really worry too much about it. So how long does it take for the UV to excite the carbon-4? So the UV fluctuates with time because the disk is clumpy and violent. When there's a UV flare, how much later is there than a carbon-4 flare? Let's ask the first question. How long does it take for a UV photon to get from here to here? What's that? Speed of light divided by R. So this is R. And the time is going to be C divided by R. Is that right? No. Does that make the units make sense?
Yes.
Yes. Always check the units when you're done, because otherwise you screw it up. And units are a really nice quick check to know whether or not you write things upside down or not. So time is radius over velocity. That's how long it takes. So that's cool. So this gives me a measurement of the distance away from the black hole that the broad lines are, right? Now, that's cool. What else do I know about the broad lines? What was the first thing I said about the broad lines? They are broad. Why? No. I said specifically that it's not temperature. It's really hard not temperature. It is? It's the kinematics of the blob of gas doing what? Spinning around the black hole, going around the black hole, orbiting the black hole. It's probably spinning, but I don't care about that. It's orbiting the black hole with a velocity at a radius. Now, there's one equation that I've written down like 400 million times. V squared equals gm over r. Given a broad line orbiting a black hole, the unknowns are v, r, and m. But here I have a really nice way to get r and a really nice way to get v. What are the hard things to measure? Mass and distance. This gives me a measurement of the mass of the black hole. So I can measure the mass of the black hole by listening to it, by looking at when the middle lights up. A little bit later, the end lights up, and I know the velocity because of how fast it's spinning around. So I can get a really accurate estimate of the black hole mass. That make sense? This is dope. This is really cool because it uses time domain astronomy, which there's not a lot of. It's really hard to do time domain astronomy because my time I have to get the project done before the grant finishes in 3 years. So everything that I do has to be less than 3 years, but some things that happen in astronomy take millions of years to occur. But this doesn't. This only takes like a couple of days. Now it's still a hard measurement to do, but this is really cool. So reverberation mapping. Let me write all this down. Summarize these ideas. So the way reverberation mapping works. UV photons at the center of the disk. Maybe not center, maybe inner. What's at the center? We have no idea because it's inside the Schwarzschild radius, so the center is opaque to us. So UV photons at the center of the disk excite line photons in the BLR, in the broad line region, at some distance. Actually, let me do this again, slightly differently. I want to organize this thought a little better. Okay, fluctuations of the inner part of the disk. Stuff falls into the black hole. Makes UV photons. They travel to the broad line region. The reason I changed how I was writing this is because I wanted to write travel as a whole bullet point, because that's how the physics works. So it takes time between when the flare happens to when the broad line lights up. They excite the broad line region. It radiates. And we get its velocity from the spectrum. And then m equals v squared r over g. Right? We get the black hole mass. So this is cool because it's a really direct measurement of mass. And it's cool because it's time domain astronomy, which is fun. And it's cool because it's things rattling around inside these really, truly massive objects. So the way of what this looks like, so here's my spectra from a couple of different days. So this is the spectrum on one day. Here it is. Actually, this tells me what it is. This is Julian day 7,582 versus 7642. So this is like 80 days later. So a chunk of days later. You can see that this object got a lot brighter, and both the lines and the continuum got brighter. But if we look at several different spectra, so this is a bunch of spectra, and they're all tied to have the same time coordinate. So this is the total flux in these quantities. So this is FO 1360. This is a broadband filter that's centered on 1360 angstroms on, I want to say Hubble, but I don't remember which telescope that's on. I didn't write that down. You should write these things down. So this is a continuum, our continuum UV uh, filters. So this is broad. This is line emission. So this is Lyman alpha, and this is carbon 4, and this is, I don't remember what FES is, but these are line emissions. And you can see that here's the continuum emission. Let's just look at this line. You can see that the Lyman alpha and the carbon 4 happen later than the peak of the UV emission. Does that make sense? That distance, the distance from this peak to this line, that's the flight time of the photons. Make sense? So, here's more of that. So, to really do the math, you look at the time correlation functions and the cross correlation and the autocorrelation functions of things. So, there's heavier math than what I'm going to make you do because I don't care. I want to get at the core of the physics. The simple thing to do is just measure the time between this peak and this peak, so this time here. So you get the radius, and then you get the velocity from the spectrum, and then you just do a little algebra. There's more complicated algebra that one needs to do to get it actually right. We're doing 0th order algebra. This is simple algebra. You know, we're not going to worry too much about the actual geometry of the thing, where the photons are hitting or whatever. We're just going to do it coarse. So the way the problems are going to look is I'm going to give you a time scale between when the UV lights up and when the line lights up. Use that to get a radius. And then we'll get a velocity from the spectrum. And then GM over R equals V squared. This is the last step in a lot of things. So these are the things that you need. So you need delta T from spectra, V squared from the spectra, delta T. So the delta T actually is a hassle to make. Why? Because the UV continuum is in the UV. How many UV telescopes are there?
None.
There's Hubble and a couple others, but there really aren't very many. UV's hard for astronomy. And the rest of these lines are not in the UV. Some of these are in the radio or infrared. So you need 2 telescopes parked on a thing for a while. So it's a hard measurement to do because it takes a lot of telescope time and it takes multiple telescopes observing the same object at the same time. So it's tricky, but it's really great because it really gets you the mass of the black hole. Let me have any questions on that? I like reverb mapping, so make sure that that makes sense to you. It'll show up. Okay, narrow line regions. Most AGN have narrow line features, not BLX. So what's up with BLX? Let's talk about that in a second. So okay. So they have forbidden transitions, which means the density is really low. The broadline region has semi-forbidden transitions, but not forbidden transitions. So that means the density is in the middle, it's intermediate, like 10 to the 6. I realize now that there's a shortcoming in these notes that I should have better densities on the broadline region. The narrow line region comes from lower density gas than the broadline region. It's further away from the black hole. So the narrow line region is the stuff that's hanging around but not orbiting the black hole. If it were orbiting the black hole, it would be broad. So we've got this picture where we got a disk, we got fluffy stuff, we got our broad line regions, we got a jet, and it's all surrounded by some stuff that's lit up by the central black hole, but not in orbit around the black hole. It's just held up by its own gas pressure. So the orbital dynamics aren't holding this gas up. It's just sitting there, held up by its own pressure. So, you know, it's going to do something like 1 over r squared because that's what gas blobs do, is they make 1 over r squared spheres. These objects are too large for reverb mapping. They seem to come from regions that are about 100 parsecs across, which means that we got to wait 100 years for the fluctuation to show up. which is too long because my grant runs out and they close the telescope. So we can't do reverberation mapping on that. So why are the lines narrow? It's not hot, and it's not fast. That's it. Lines get broad because of temperature and kinematics. So it's cold gas, relatively cold gas, that's around the black hole, but not in orbit around the black hole. So here you can see this is a broad line. This is hydrogen beta, and this is this forbidden oxygen, which is super, super narrow. Yeah. So when we're looking at the zoology, Seifert 1 and Seifert 2 are both AGN. Oh, I should put this over here. Seifert 1 and Seifert 2 are both AGN. Why is that not working? My image is black. My apologies. Why is that not working? I can't tell. The problem is I can't tell. I can tell that OBS doesn't like what I'm doing, but I need the things to show up for you guys. Let's try. Now it works. I have no idea why that. Okay, now that one works too. Jesus Christ. Okay. Sorry. Now the camera shows up. Okay, so Seifert 1 and Seifert 2 are both kinds of AGN. A Seifert 1, see, it has this hydrogen beta line that's really broad. Here, the hydrogen beta line is really narrow. There's Seifert 1 versus Seifert 2. So why? So actually, I got this image of the broad line region. So here is a galaxy from the ground, and here's the HST image of it, and you can see this is a cone of stuff that's getting kind of blown out by the AGN. So how come I have a Seifert 2? So why is H beta so weak here? It's hydrogen. It's not like there's not hydrogen there, right? There's hydrogen in all of these things. Hydrogen's everywhere. So it's not that the hydrogen line is less because there's less hydrogen. It's less because there's stuff in the way. So this is where this two family picture comes from, or two parameter family comes from. So this is what the object looks like. And this is where the broad line region is, and this is where the narrow line region is. It's right here. So if I'm sitting over here, my line of sight is blocked by this stuff. So I can't really see the broad lines, but I can see the narrow lines. Does that make sense? So that's the big difference. And this is where these QSO, the type 2 QSO comes from. I should be able to see a type 2 QSO, which is like a brighter Seifert galaxy that doesn't have the broad lines. And there are a couple of those, but because the QSO is so bright, typically the broad line regions shine through this stuff. So we don't see that stuff. Another way to see that this picture is correct is to look in polarization. Do I have those slides up here? I moved them. If I look at polarization, if I put a polarizer here, so light that reflects off something is typically polarized by that thing, by the geometry. If I've got a surface and a photon bounces off of it, not all of the components of the photon are going to continue. Only the components that can excite the surface can continue. So the reflection polarizes the photons. So if I look at a polarizer, I can block out most of this, but I only see this reflected gas, and I can see the broad line region in the reflected gas, in the polarized light. So if I put a polarizer on it, I can see the broad line region reflected off of the narrow line region, and I can see it that way. So that's part of how we know that this picture is right. Is if I look at a polarized image, I can see the broad line region reflected off other stuff, which is kind of cool. Okay, let's talk about X-rays. So X-rays, again, are very high energy photons. When you get towards the center of the gas, it's not thermal anymore because the temperatures doesn't last. The fluctuations don't last long enough for the temperature to get that hot. This is from really short-lived fluctuations where the temperature gets really hot and blows apart an ion and then fluctuates back down again. So feeding events where the black hole accretes some stuff makes the temperature go up, and then you get flares in the X-ray. So this is what a typical spectra of one of these things looks like. So you can see all of these lines. Look at all of these lines. These are all metal lines. So this is nitrogen 6 and carbon 6 and oxygen 7 and iron, what is that, 17? Okay, iron 17. How many electrons does iron 17 have? How many electrons does iron have? What's the atomic mass of iron? It's 26, I'm pretty sure. Right, so iron 16 has 15 electrons removed. So, okay, the first electron comes off pretty easily. The second electron is coming off of a charged object. It doesn't come off as easily. And it's lower down, so it's more tightly bound. So if you think about a tower of electrons on my iron, here's my iron. This is the electron that's going to come off first. It's pretty weakly bound. This electron is a lot more tightly bound. It's much further down in the potential well. It's more tightly bound. So taking off the 17th electron is very difficult. That means the temperature is ridiculously high. And we see it flare. So what else can we see? So here's something cool. This is the inner disk. Let's talk about this for a second. So this has some complicated pieces. So let's talk about a disk that's rotating. Think about this step by step. So let's just think about the top picture. So this is the spectrum that I'm going to see. Let's say the disk is really hot because you're really close, and remember temperature goes like R to the 3/4. So as you get in, it gets really hot. So you've got this disk of stuff that's basically emitting in the X-ray, and there's a bunch of X-ray lines, and it's violent as hell, but it's spinning like crazy. So as I'm looking at it, some stuff is coming at me like crazy, and some stuff's moving away from me like crazy, and some stuff's moving sideways. So I get this two-horn kind of picture like this, where I have a bunch of stuff that's coming at me, and then this side of the disk, and then the stuff that's moving away from me as a function of wavelength. Does that make sense? So this is what a disk that's spinning looks like. And we've seen this before, right? We saw this when we did Tully-Fisher. We saw a picture just like this. Now we got to add in all of the general relativistic effects. We haven't talked about relativity a ton here. It comes up from time to time. So the first thing we'll add is the Doppler beaming. So Doppler beaming is when something's coming at you, it looks brighter than if it's moving away from you, because it's hucking all those photons at you. The photons that would be going behind it are now coming at you. So when something's coming at you, it gets brighter. So which side of this is going to get brighter?
The left side.
The left side, because that's the side that's coming at me. It's backwards. This is in velocity. So the left side will get bigger. It's backwards from the way this picture is because this is in frequency space. This is the frequency, observed frequency. Let's do it that way. I'm going to write this as frequency just so that it's consistent with the picture. So I'm going to get something that's a lot brighter on this side because of the Doppler beaming. Gravitational redshift moves everything south to lower energy. So it goes over here. So we get this picture when you smooth it all out for reality. So we have two things. We have Doppler beaming. We have general relativistic redshift. How does general relativistic redshift work? When you leave an object, you lose energy. So as I go off the Earth, I lose some energy to the potential well that I'm leaving, right? So I've got a lot of energy now. If I leave the planet, I get less energy. Photons do that too. If I shine a flashlight up, it will get redder as it goes up, as those photons climb out of the potential well. And this is a really measurable, like it's a really dramatic effect. You can see it if you happen to have an atomic clock on a satellite, which is how a GPS works. So the GPS is about clocks that are really accurate. And so you can tell that the GPS signal gets accelerated a little bit and starts running faster when it gets to me because it falls down the potential well. If we didn't account for this, the GPS would only have an accuracy of like a mile. So we got to account for that, and we can get accuracy of a couple feet. So anyway, gravitational redshift and special relativity give us this. And then we can see it. So this is an actual measurement of X-ray lines off of one of these disks, and you can see that the flux has this same two-horn shifted half amplified. Did I talk about this bit? Have I brought this up before? So did you guys see this movie, Interstellar?
Yeah. I need to see it. Everyone told me I need to see it. I've never seen it.
Oh yeah, so it's pretty good. I enjoyed it as a film. Yeah, so anyway, one of the nice bits about it is this magnificent visualization of this black hole. So there's, in the movie, there's a huge black hole that they orbit. I don't think I'm giving away anything by telling you there's a huge black hole in a movie called Interstellar. But this guy, Kip Thorne, I think that it was his idea. I think that it's his story. But he was one of the science advisors, and he successfully kept faster than light travel out of the story, which I'm very thankful of. Sometimes you got to invoke faster than the speed of light when you're writing a sci-fi story. And that's fine, because space is too big to make a story otherwise. But the less you can, the less of that you have, the better. I knew a dentist when I was in grad school he was trying to write a sci-fi story, and he was like, I really need some physics that'll let me go faster than the speed of light. And I'm like, no, I'm not going to help you with that, because every time they try to make it too physicsy in the story, it sucks. All the time, every time. When you try to invoke too much physics, just make it a magic black box so you can go faster than the speed of light, you can communicate over there. Ursula K. Le Guin invented the Ansible in the 70s, so you can communicate anywhere. We can just use it. So anyway, faster than light was not in that movie, but there's a lot of cool physics that was. And part of the cool physics is this visualization, which is a really great visualization of what you would see around a black hole. So what are we looking at? We're looking at this disk of stuff that's in orbit around the black hole, and then this hole, which is the black hole. And then this stuff over here, why is there stuff on the top?
It's from behind.
That's from behind. So this is the back side of the disk. So the disk looks like, oh man, I wish I had a hat. The disk looks like a pancake with a bowling ball in the middle. And the photons on the back side, you can see because they go up and they hook over that way. Yeah.
What if you look at this instead, like from overhead? You know what I mean? Is the spinning just like on one axis?
Yeah, and the disk is in one plane. And if you see it overhead, you'll see the same thing.
Oh, okay.
They kind of look the same from whatever direction you look at.
Okay.
Which I kind of hate. So the only piece of physics, there was a cool paper that came out shortly after this paper that came out that said, here's what the visualization actually should look like. If you include the Doppler brightening, and that's basically the same thing, right? That's really this very similar picture. So that's very cool. Beaming, I'm not going to talk about the math of beaming because I'm not going to make you do it. Okay, so get your head around the components of the AGN spectrum. So in the radio, We get synchrotron, and that comes from the jet and all the stuff along the jet. In the UV and optical, that's continuum radiation and thermal radiation from the black bodies that are the disks. So there's a disk, it's got some temperature, so we can treat that as a couple of different portions of disk, and the different portions give us different black bodies. Of the broad line regions, which is further out, little fluffy clouds around the black hole. There's a super famous techno song called Little Fluffy Clouds that came out in the early 90s that if you listen to any electronic music you've heard, but gets stuck in my head for the entire week that we're covering AGN, because every time I say Little Fluffy Clouds, this piece of techno starts playing. Anyway, the narrow lines, which is just the stuff that's in pressure support around the black hole, but not orbiting, not rotating, not hot, not broad. And the X-ray is the stuff that's at the very center of the black hole, and it's hot as hell because the disk is just hot as hell there. And it's violent and fluctuates, and there's all these lines. And you can use that to really probe the general relativistic and special relativistic effects of the disk motion. So those are really cool. So AGN are very cool. Oh, here's my cartoon for the polarization. So I think that this has only been done a couple of times because everything has to line up just right for the observation to work. But this is NGC 1068, the total flux, and this is what happens when they put a polarizer on it. And you can see how much broader this line is. It looks a lot brighter. This one still looks narrow, but this one looks a lot broader. Notice that the flux is weighed down by a factor of 100 because we put a piece of plastic in the way. But you can see this is a lot broader because this stuff is in the way, but this broad line region bounces off the dust and the stuff that's in the narrow line region, and then you can see it. So it's kind of a funny measurement. But what this shows us is that in AGN that don't have a broad line region, it's not because it's not there. It's because you can't see it. That's the important bit. Do I care about any of the rest of these? I don't think I do. So we did reverb mapping. We did the rest of the spectra. What's next? I got 20 minutes left. Jets. Fine. Oh yeah, okay. That's what I got to do with my remaining 20 minutes. Jets. So the last piece we want to talk about is jets. I think this is I think that this is the last piece of AGN. No. There's two more things in AGN I want to talk about. I need this one too. And this one's just going to go real fast. I'm just going to show you a cool picture. But I do want to show you that. Okay. So this is kind of an unsatisfying discussion of jets because they're much cooler than all of that I'm going to say. So this is M87. It's one of our favorite galaxies. This is the one where we measured the black hole for the first time. So the Event Horizon camera took a picture of the black hole around here for the first time. We like M87. It's pretty close. The optical jet is 5,000 light years long. And there's a radio jet that is 20 times longer than that. It's 100,000 light years. So that means that this thing has been squirting out in a straight line for at least 100,000 years. Probably 4 or 5 because it's certainly not traveling at sea. So for 500,000 years, this thing has been just shooting this stuff into outer space. Oops. Somehow I broke my thing. Let me get it back. So this is what, and this is, I didn't go through, did I go through in detail how to measure magnetic fields this year? I don't remember. I don't think I did. I spent a minute on it, but not a ton of minutes. There wasn't a homework problem on it. Yeah. So I talked about it, but I didn't harass you about it. one of the ways you can measure magnetic fields, I talk about it because I think it's interesting, and I don't talk about it as much as I want to because it's not super relevant for like dark matter and stuff. But this is really great. This is again from the Event Horizon Telescope, and this is M87 with the Event Horizon Telescope. And the stripes are the polarization, and the polarization lets you measure the magnetic field because sorry. Was that?
You see all the, I guess, turbulence of the magnetic field?
Yeah. So when you have a magnetic field, a dust grain is kind of a blobby, elongated thing, kind of like a candy bar, like a lumpy, like a payday bar. And they're charged because the UV photons. UV photons ionize these dust grains. They kick off electrons. So we got these charged objects, and they're going to line up with the magnetic field, just like iron filings. If you ever play with iron filings in the magnetic field, the dust grains do that. Dust grains just line up. So when I see a strongly polarized signal, it could be dust grains that are lined up, or it could be hot electrons that are spiraling around. So dust gives me polarized light in the face of a magnetic field. Synchrotron electrons also give me polarized light in the face of electric fields. So here, this is the jet, this is the HST jet. So I didn't think that Hubble had a polarizer, but they just turned it on like a week ago, which is fascinating to me because it's clearly been up there on the object for a while. So I don't know why they just turned it on. Like, why do I have access to a polarimeter now? But anyway, so this is the polarimeter. I think this must have been from Hubble's polarimeter. But anyway, you can see the magnetic field's kind of perpendicular to this thing, and it's kind of going along. It's kind of a little turbulent. Here you can see the magnetic field is kind of aligning up along the disk as it gets dragged around. Here we have some more jets. This is in the radio. They're pretty great. So what's happening? So here's a cute cartoon. The spinning of the disk and the differential rotation of the disk spins up the magnetic field like a corkscrew. And then that corkscrew works like an Archimedean screw to just squish stuff out, like an auger, like a drill. It just cranks on the material and it throws it out. It's kinetic, not so much as an auger. One of the cool things that you can see is this motion. So we can sort out how fast this jet is moving by watching these blobs. So here's a time series of one of these jets taken from 1994 to 1998, and the AGN is at the center, and you can see this blob, bloop, 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 and this blob, bloop, 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 and this blob, bloop, 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 bloop. These blobs moving out. Okay? And we can sort out how fast they're going by saying dRdt. So I have this thing, and this was a big argument in the late 90s, early 2000s, because people saw these, and so this guy goes like, time goes this way, and here's the center. This line gives me d theta dt. How do I get a velocity out of that? Theta is the angle on the sky. How do I turn this into a velocity that this is going in this direction? That you multiply by the distance. So v is d times d theta dt. So they did this for some of these jets, and they got 5c. Not like 1.5 c, but like a lot bigger than c. So this was still in the age before WMAP and the age before Planck and the age before all of the people who really hate the Big Bang had died. So some of them were still alive and kicking. Most of the real dissenters of the Big Bang have passed on. His time. I saw this. Okay, do you guys know who Philip Glass is? Sorry, you're going to go on a journey of this squirrel brain. So Philip Glass is a composer. He's a super important composer. Writes minimalist music. He gave a talk here and played some. It was really great. Maybe 4 years ago, 3 or 4 years ago. So he plays this. He writes this music and was writing this music in the late '60s and the '70s, and he's still writing music now. But people hated it because it's really challenging to listen to, especially if you've never heard anything like it before, because some of it is just like the same note over and over again for like 20 minutes. He's not that bad. Lamont Young is that bad, but he plays this music that's pretty challenging to listen to, and there were all of these critics that hated his stuff and said, "This isn't music. This is crap." And so he talked a little bit in his talk about that, about how all the critics really hated his work. Now he's clearly one of the most important composers. Like, everybody loves his work. He's stood the test of time. So he had this question and answer session, and one of the questions was, the student asked, "How did you win over the hearts of all of the critics who hated your work?" And he said, "Oh, they didn't change their minds. They died." So progress happens as the old guard dies. So anyway, the Big Bang is really well established. There's no question in astrophysics anymore that the Big Bang happened. But before it was really well established, which was only like a couple of years ago. Like, this is relatively recent. Like, this is in the early parts of my grad school, I was hearing this kind of story. Because what does this say? This says that this can't be right. This says that because we measured this distance, d, we got as v over h naught, right? Because we assume cosmology. So this says that that distance is way wrong, right? That's what that says. Or it says that you didn't do the special relativity correctly, which is actually what it says. But this is what, the reason that this is in the book, the reason that people talked about this is because it was a huge ding on the expanding universe, because we had these jets that were clearly going faster than the speed of light. But they're not, people just didn't do the special relativity right, because you generally don't need to, because you don't usually look at things moving like this in astronomy. So the fact that it's moving while you're taking the image doesn't matter for a lot of things, but for this it does. I'll explain. So the book does a terrible job with explaining this. The Wikipedia page on this does a better job. But it's special relativity, so it's still confusing as hell. So let's talk about it for a second, and that's going to be what I talk about for the day. So I have a QSO here. And I have a blob of stuff that's moving in this direction. And I am down here with my hat. That's not the hat. That's my hat. It's wintertime, I'll wear my beanie. So this is the line of sight, and this is the other line of sight. So let's draw a better, slightly more exaggerated picture. I'm down. Here's my AGN. Here's my glob. Here's me. Here's me. This part is where, this part here is the tricky part. Because when I take a measurement like this, I'm assuming that these photons from this blob and this blob were released at the same time and then traveled and got to me. but they were not. The photons that I get now were released from this guy earlier than this guy, because this guy released some photons, and then this guy went way, way, way far ahead, and then released his photons, and they look like they came out at the same time. That makes sense? So I'm hiding a lot of the time of the photon flight in the motion of this object, because this object is moving relativistically. So let's do a little math. Okay, so a photon is released at t1 from this blob, and at t2 from this blob a little while later. Oh, where's my cartoon? My cartoon is better. Did it this morning. Okay, so T1. So T1 is when the photon is released from the QSO, and T2 is when the photon is released from the blob that's in the jet. Why are jets blobby? Because accretion is blobby. Accretion is stochastic. The accretion doesn't happen in a smooth manner. It has chunks and blobs. Chunks and things that should otherwise be smooth makes me uncomfortable. So there's blobs because the disk system is chaotic. So I'm going to measure this photon at T1 prime and this photon at T2 prime. T1 prime is T1 plus, let's call this D, and we'll call this D. This angle phi is really small, so the two D's are the same. I can do that without losing much. So the first photon gets to me at T1 plus D over C plus, oh, let's see, how much is this? So this object is moving at a velocity v, so this is an angle theta. This distance is v cosine theta times delta t. T2 minus T1 is delta t. That's the difference from when the photon was emitted initially and the photon was emitted afterwards. So this distance here plus v delta t cosine theta. And T2 is T2 plus d over c, but it doesn't have to have this v cosine theta. That's where the magic shows up. Is this guy hides a lot of the motion of this. So the time difference in my frame between when this photon went off, when I get this photon and when I get this photon, is delta t when they were emitted minus v delta t cosine theta. Then just take the deltas of these two things. The only thing that's different is that. Delta t prime is the time that matters for me because I'm the observer. This is when the photons are getting to me. So we can say that delta t equals delta t prime over 1 minus v delta t cos theta. Oh, v 1 minus v cosine theta delta t cancels out. Got a dt and a dt, and that cancels out. Right, so this is really the important bit. V cosine theta. Oh, that's I need to over c. Over c. Sorry. I'm going to v over c cosine theta. So this term is strictly less than 1. So this guy is big. Yeah. Yeah, totally. I want to keep all that. I like these boards. Okay, so the velocity, so from in this direction, so this is delta t times v sine delta t v sine theta. That's in this direction. But what do I experience I don't measure that. I measure phi sine theta over a delta t prime. That's what I measure, right? So this is the sine theta over 1 minus beta cosine theta. We divide this by c, and this becomes beta. So beta b over c. So the apparent velocity that I measure has this extra 1 minus beta cosine theta because of this flight time of the photon while this guy is going. Since this guy is going, covers a really substantial amount of distance while this photon is traveling, that's why it looks like it's traveling faster than the speed of light, because it hides a lot of its motion in the flight time of the other photon. That makes sense? This really makes the most sense once you've actually sat down and done it for yourself. So either you can forget about it or there will be a homework about it. I haven't decided that yet. That's all I got for the days. And yeah.
Are you saying that we also measure the first photon, like at T1, and the other photon at T2? Like I was thinking, if the blob is moving, then wouldn't that photon kind of disappear?
Which one?
Like the first blob. So like you see.
No, you'll get it.
You still get it.
Yeah, you'll. I mean, I get both photons.
Yeah.
What do you mean disappear?
Well, T1 prime and T2 prime are the same, right?
That's right. That's when I measure this guy versus this guy. That's right. The result though here is the important bit, is that you get this 1 minus beta. The thing that the takeaway is, you need to be very careful. So I had said T1 prime is here and T2 prime is here. Doesn't make a huge difference. I could say that T1 prime is this one. I still have that same problem of these two things, even though I took a picture at the same time. So I took a camera, or my camera took a picture of these two blobs at the same time, but they're not at the same time where they are. One of those photons was released a little sooner, and the other one moved, and then released this photon, and they look like they came to me at the same time. Does that make sense? So the travel time is important. The three-dimensional.
So this is related to the beam, right? So like, since it's moving in this direction really fast, all of the photons are kind of moving in that ish way.
It's not a photon beaming problem. That's a statistics problem. That's a counting issue. This is just, it moves while the other photon is moving a lot, and that's the important bit. Okay. Have a good weekend.